Welcome to part 2 of the exercises of lesson 4. And now we are with exercise 4.8. Question is, we have a few propositions. So Px, Qx and Rx. Propositions. We have a few propositional functions. P is a function of x, Q is a function of x, and R is a function of x. And they will become propositions when x is given a specific value. Write the statement in a symbolic form. Let's look at question A. There exists an integer, so there is an integer x, so we name it x, and we know it's an integer, so it's from z, in such a way that x is even. Well, we have a propositional function, Qx, which says x is even. So we have now translated it in a nice mathematical way. And now it also has become a proposition, because with the existential quantifier, if I can find only one x in this domain for which Qx is even, then the proposition is true. Well, that's of course not a problem. Take 2, 4, minus 6, whatever. So that is true. Question B. There exists an integer. Okay, there exists. We name it x. Again, it's an integer, so the domain is set in such a way that if x is even, then. So there's an implication. X is even is again the function Qx. Implies, so if Qx, then Rx. X is divisible by 4. Okay, then let's see if this is true as well. So is there an integer x in such a way that Qx is even implies that x is divisible by 4? Well, this is a trick question, because of course you know that when we start from a false in an implication, then the complete implication is always true. So let's just take one odd number. For example, x is minus 3 or x is 5. And then the implication is always true. So again, this one is true. Last one, for all integers. So for all, we name it x again. X from the domain z. There exists, so there's a next quantifier. There exists an integer y, so the name is y, coming from the domain z, in such a way that x divided by y is divisible by 4, so that the function r applies to x divided by y, and x plus y is even, so q x plus y. Looks complicated, let's not forget the last bracket. Looks complicated, but if you just go from the left to the right, take a deep breath, then it is doable. Now we only need to look at the last statement to see whether it's true or false. And with a universal one, it's always tricky. If it's true, then you need to prove it for all elements. So let's hope it's false, because then we only need to give one counterexample. So for instance, if I would take x being 3, then I need to find a y in such a way, and this y is coming from the domain z, in such a way that 3 divided by y is divisible by 4, and that x plus y, so 3 plus y, is even. Okay, now let's look at the first one. 3 divided by y is divisible by 4. If I have y being an integer, then 3 divided by that one is never divisible by 4. So I already found one counterexample. So the complete proposition is equivalent with false. Exercise 4.9. We need to examine whether a proposition is true or false. Let's have a look at the first one. There is an element x coming from the universe, and the universe is given by 2, 3 until and including 8, in such a way that 2 times x larger 10. Okay, no problem. That is true. Let's just take, for example, x being 7. Then 2 times 7 is 14, larger 10. B. For all elements coming from that universe, it applies that for all elements coming from the same universe, that x plus y equals 4. So it's a universal quantifier. Let's try to find a counterexample, because then we're easier done. We're faster done. So let's take x being 6. Then can I find, well, is it true that for all y from the universe x plus y equals 4? I can't even find a single one. Let's leave alone all of them. So this is false. One counterexample applies. Last one. For all elements coming from the universe, there is an element coming from that universe that x is smaller than y. That's more tricky, because now if I look, for instance, at x being 2, yes, then we can find a y from the universe in such a way that 2 is smaller than y. And so the critical part here is the smaller than. So let's try 8. That's the largest one possible. So if x is 8, can I now find an element from the universe in such a way that 8 is smaller than y? And then the answer is no, I can't. So C1 is equivalent with false. We found a counterexample. Again, a mathematical induction question. So we have a sequence with definition. So R1 equals 2, and Rn plus 1 is n plus 1 plus R1. So let's just look what it means. So R2 would be 1 plus 1 plus R1. So that would give us 2 plus 2 would give us 4. R3, that would mean it is n plus 1, so that would be 2 plus 1 plus R2, so that would be 3 plus 4 would be 7. R4, so that would give us 3 plus 1 plus R3, that would give us 4 plus 7, that would be 11. Prove with the help of the mathematical induction that for all numbers, whole numbers, so integers, and we start at 1, so larger equal 1, that this Rn equals a half times n squared plus half n plus 1. Step 1. Well, we know this. Step 1. To prove it's true for the first element. So the first element is R1, because n is larger equal 1. So we need to prove that R1 equals a half time 1 squared plus a half time 1 plus 1. So we need to prove that R1 would be a half plus 1 would be 2. Okay, given with the definition, R1 is 2, according to the definition. So 2 equals 2 question mark. Yes, check, done, no problem. So the first step was administration again. Let's continue with the second step. So step 2. And then we need to start with an assumption. So assume that the statement is true for some element in the middle. And let's make the assumption blue again. Let's call that element in the middle k. So assume that rk equals a half time k squared plus a half time k plus 1. For some k in the middle. so larger than the first element. So we need to prove that it's also true for the successor, so that rk plus 1 equals a half time k plus 1 square plus a half time k plus 1 plus 1. Let's simplify this one immediately. So that would be a half time k square plus 2k plus 1 plus a half time k plus a half plus 1. So that would give us a half time k square plus k plus a half k, 3 divided by 2k, plus a half plus 1 plus 2. Okay, so we need to prove that rk plus 1 is a half time k square plus 3 divided by 2k plus 2. Let's try. So, proof. We start on the left. So rk plus 1 equals. What do we know about rk plus 1? We know something because of the definition. So we know that rk plus 1 is k plus 1 plus rk, because of the definition. Then we know something about rk because we have an assumption. So rk is a half time k square plus a half time k plus 1. I use the assumption. Okay, then try to make it in a similar shape as the one we tried to prove. So let's put the k squares up front, so that would be a half time k square. Then I have a k and a half k, so that will give us 3 divided by 2k. And we have 1 and 1 plus 2. Okay, lovely. Look, we needed to prove something, and it's identical to the one we have proven, so we're done. Now, with the help of mathematical induction, we have proven that indeed Rn equals a half time n square plus a half time n plus 1. Okay, those were the exercises of lesson 4. Next video we'll talk about the exercises of lesson 5.